Okay. So your work has been returned to you, marked already. I think there are 2 students who still have not submitted their work for marking. It is all being recorded down. Okay, let's look at the first one. The source of the rope wave is the up-down motion of the hand. This up-down motion is known as vibration. So everybody actually got all this correct, vibration. The vertical arrows, just talking about the motion of the particles moving upwards, downwards. And the horizontal, this arrow, represents the direction of the wave. It is moving sidewards. So we see that all these up, down, and left, right, they are perpendicular to each other. Okay, back to this. The rope wave carries energy from one end to the other. So as it carries the energy, do the particles move from left to right? You see, over here, he started off with this part, he started off with a flick, right? So this flick over here, this crest, actually travels moving to the right. So that we call it the wave is moving to the right. But is the particle in this rope, is it moving to the right? Is the particle moving to the right? No, it is not. It's only moving up and down. So that is why we say waves, they carry energy from one point to the other without any transfer of the medium. In this case, the medium is the rope. If we talk about sound, for example, Mr. Wong talking right now, you can hear it, right? It is actually a sound wave traveling towards you. What is the medium? What's the medium? How is the sound traveling towards your ears? Yeah, but what is the medium? Air is the medium. Okay? It is the air particles that are vibrating as I'm talking. When they reach your ears, based on how the air is vibrating, you make sense of what I'm saying. What if there's no air? Can sound travel without air? Yeah, so it's a vacuum, right? So in space, you watch the movies, in space there are explosions, right? Should there be a sound that you can hear? You shouldn't be able to hear anything. But there is sound already. Yeah, so it's just really like that. No sound at all. Because there isn't a medium for the sound to travel in. Now, not all waves require a medium. For example, our infrared radiation, we learned in our transfer of thermal energy, right? We say that it can transfer without a medium. So through a vacuum, our Earth gets heated up by the sun, the sun's infrared radiation. They do not require a medium. So likewise, light. Light is also a type of wave. Doesn't require a medium. Okay? What about water waves? Do they require a medium? Obviously, water. Water is the medium. Okay? Okay, now, which of the following figure represents a longitudinal wave motion? So this is the other type of wave. Most of the time, we only talk about most of the waves that we know of, they're all transverse. In our syllabus, we are only concerned with one type of longitudinal wave. What is that? Sound wave. That is the only longitudinal wave that you need to know in your syllabus. Okay? And longitudinal wave, the particles, they oscillate parallel to the direction of wave. See, they are parallel. So this one is longitudinal. Whereas this one, vibrating up and down, but the wave is traveling to the right, they are perpendicular. So this is transverse. Take note, we are only talking about one particle over here. One particle. Okay? So what is the name of the other type of wave motion? Obviously it is transverse. State one similarity. So I mentioned for our textbook you have 3 points. The complete answer will be as such, and I asked all of you to copy it down. I said it just now also, transferring energy from one point to another without transferring the medium in which the waves travel in. Right, so just now I mentioned about air being the medium, right, when I talk. So when I talk, the sound travels towards you. But if you were to look at individual particles, air particles, if you can see it, they're actually vibrating parallel to the direction of wave. So in and out, left and right. But the particles don't travel all the way there. It is because one of it vibrates, causing the adjacent ones to vibrate, causing the adjacent one to vibrate, so on and so forth. Okay, like your slinky. If you remember the spring toy that I brought, I do a flick on one side, then there'll be compression seen. So they'll compress and expand. The word for this expansion in a wave is called rarefactions. Later we see how to spell it. Compress, rarefaction, compression, rarefaction. Keep on repeating and repeating. So examples like I mentioned, all of it will be transverse. In your syllabus, only some wave will be longitudinal. Okay, 10B. Have you all done it? Yes? How do you all know that you are supposed to do it? Yes, it is written in Google Classroom. We are supposed to do 10B and 10C so that we can discuss today, and also to bring our TYS, right? So for those who have done it, please take it out. For those who haven't, try and follow. Okay, 10B, take it out. This is a transverse rope wave. Then what do C and T represent? C over here is the highest point. So they are the crests. Okay? And T, the lowest point, we call it a trough. Know how to spell it. These are very important keywords. Next, what does A represent? A over here is the distance from rest. So this line over here, rest position, to the highest point. What does it represent? Amplitude. Is this distance over here the same as this distance? Yes, they are the same. It's also the same as this distance. Okay? And one more thing is that I mentioned, if for example this is maybe 8, then how much is this value? Negative 8. Don't forget the negative sign. Okay, then what does X represent? Okay, the answer is already given on the screen. It is the wavelength. So how do we know whether it is a wavelength or a period? Because period also seems to be on the horizontal axis. Right? Remember yesterday I drew on the board and I said that this over here is the period. Also right, I drew something like this on the board. So how do we know whether it is supposed to be a wavelength or a period? That's why we need to look at the axis. For this one over here, it is a displacement, this time graph. For this one over here, it is a rope wave. So they are showing the actual rope and then carrying the wave, and then they take a picture. So this is what you will see. So this is again displacement, and this will be our distance. For example, I hold a rope over here, Jianzhou at the end, he holds the other end of the rope, I flick it, then somebody takes a picture while the wave is traveling towards him. This is what he will see. So Mr. Wong here, so Jianzhou at the other end. Okay? So displacement, distance graph, the distance between one complete wave is known as the wavelength. Any questions so far? Can I take a picture of this graph? Is it possible to take a picture of a displacement time graph? Cannot. Your camera only can take 2D pictures, right? It cannot take a time picture. Okay? So let me erase all of this. Okay, so quick recap. Since we say that this distance x equals to the wavelength and we use this symbol to represent it, lambda, can you tell me what is the distance over here? What's the distance? Is it also lambda? Yes, it is one complete wave. Look at this. This one, if you repeat this red color portion over and over again, you will get the complete graph. Okay, what if I were to choose maybe this point to this point? Do I get a complete wave? Yes, I do. Just repeat this one over here. Okay, see, it is repeating again and again. So the distance over here is again lambda. I can choose any other points I like. For example, maybe this point and this point. So this is the wave I get. If I repeat it again, I will still get another wave. Okay? What do we call these points? For example, this one and this one, we know that they are called a crest. For example, this T over here and this T over here, they are called a shroud. As long as they are adjacent, for example, this point, okay, let's choose an easy one. Maybe this point and this point. Okay, these two, they mark the ends of one complete wave also, isn't it? These points, they are known as being in phase. In phase. That means they are behaving in the same way. Both of these 2 points, if one is moving up, the other is also moving up. If one is moving down, the other is also moving down. Okay, because they are the ends of the same wave. Okay, just like your crest. All of your crests over here, and if I were to continue, all of them, they are all in phase with each other. Then all of the trowel, all of them, they are all in phase with each other. If one goes up, the other goes up. One goes down, the other goes down. They behave in the same way. Okay? Okay, let us consider the following statements. Number of complete waves produced per second is the frequency. Okay, we derived it. We talked about the equation yesterday, and then the unit for frequency is hertz. H-E-R-T-Z. Know how to spell it. And in the symbol used is Hz with a capital H, a small z. Symbol for wavelength is lambda. Distance moved by the point on a wave in 1 second is known as the speed. So look at this. Distance moved in 1 second. Isn't that speed already? Distance moved per second. That's our speed. Time taken for one complete wave is period. Okay, all definitions, you need to know the differences between them. So as I go, please do your self-marking with your green pen, corrections with your green pen also. So speed V equals to F lambda. This is our equation that we will always be using when calculating speed, frequency, and wavelength. As long as you have 2 of these, you can find the other one. Okay. So this one, basic calculation, using V equals to F lambda. For the first case, if we don't know the answer, this is going to be equals to 4 times 0.5. Of course, you have to check that they're all in SI units. So then my answer will be 2. And this 2 will also be in SI units, meters per second. That's for the first answer. Okay? Now for the second part, I'm given V and F. So I need to find lambda. Using my equation, simple mathematics, lambda is equal to V over F. Substituting accordingly, 150, this is in centimeters. Let us change it to SI units. Okay, this will be 1.5 meters per second. So I have 1.5 divided by 10. 0.15 meters. We always try to work in SI units. Now if you left your answer as what they have over here, 15 centimeters, it is still correct. But to make things easier for us, we always make it a habit to write in SI units. So that whenever there are conversions, your final answer will still be in SI units. And now, for the last question, we are given the speed and frequency. Now to find lambda will be equals to V over F. So 3 times 10 to the power 8, which is actually the speed of light, divided by 4.3 times 10 to the power 14. And then you will get this answer. Okay, approximately. Why? Huh? What do you mean I write the answer? Oh, sorry. Eh? What am I doing? Sorry, wrong. We are trying to find frequency. Okay, so frequency equals to V over lambda, which is actually 3 times 10 to the power 8 divided by 7 times 10 to the power negative 7. So then you will get this answer. Okay? What do you notice about this number over here? Is it a big number? It's very big, right? If you were to write it out in full, there will be many digits. What about this number over here? Very big or very small? Very small, right? If you were to write it out, there will be again a lot of 0.000, so on and so forth. And this number, very big. Many digits. So instead of writing so many digits, what form do we use for these three numbers? Yeah, standard form. Now you see how standard form is being applied in physics also? You should see it in chemistry as well. Okay, then now the equation linking frequency to the period. F equals to 1 over T. Derived for you all yesterday already. This also means that T, the period, equals to 1 over F. Same thing. Okay, now. Question 4. This is a figure that is drawn to scale. It's a wave traveling along a spring. So like my demonstration to you the last time, you see regular intervals. If you were to describe it, this part over here, they are the compressions, right? Compressions. And then the parts that are expanded, like over here, here, they are called the rarefactions. Okay? They occur at regular intervals. Now measure and record the wavelength lambda of the wave. Where is one complete wave? Because wavelength, this talks about the distance of one complete cycle. Okay? So where is one complete cycle? Can you identify very clearly from this? Where do we start measuring from? Where do you want to start? Shall we start from the compression? Because I think it is easier to see the compressions. Shall we start right from the center of the compression then? Maybe let's start measuring from here to here. That is one complete wave, right? So can you take out a ruler, measure this distance? What do you get? Since it is drawn to scale. Brian, you don't have your book. Are you listening? You're not even watching. How do you know what I'm talking about? Without looking. But you didn't look. How you know what I'm talking about? If you really want to do well, you need to at least listen in class and look at what I'm doing. Okay, what did you all get? 3. Okay. Although it is drawn to scale, there could still be human error when you measure. I would like you to measure the distance from here to here as well. Is it still 2.9 to 3? It should be lah. Okay. Would you like to try measuring from maybe a rarefaction to another rarefaction? Is this also 3? Yeah, okay. So regardless at which point you start, if you choose to start from here, you must end at another point that is in phase. Okay? Over here. They are in phase. So let me just draw a few more. This green color one, And this green color one, they are also in phase. So on and so forth. Now if the speed is 58 centimeters, not in SI units, per second, calculate the frequency. So 58 centimeters per second, this will be 0.58 meters per second. What is the formula that we should use to calculate the frequency? Wei Hao, what do you think? What's the formula that we'll use? Yeah. What is it? Lambda. L-A-M-D-A. Okay, it is a Greek letter. Okay, come. Let's continue. So we use this, but you don't want to memorize so many things, right? So we just memorize one of it only. We just memorize one of it, which is V equals to F lambda. We derive anything else that we require from there. So since we have V equals to F lambda, we want to calculate F, and then we will get V over lambda, which is 0.58 divided by the wavelength. Just now you all got 3 cm, right? So in SI unit, that will be 0.03 meters, 0.03. And you should get approximately 20 hertz as well. Okay, do you all get that? Okay. Any questions so far before I proceed? By the way, Jovial, can you hear me? Can you hear me? Okay. Here we have a waveform. Take note of the axis, displacement, distance. What are some of the things that I can tell from this diagram? Jia Yi, what are some things that I can tell from this diagram? The what height? From where to where? Rest position to the crest. Okay, he's saying that I can tell this value. How much is this value? 30 watt. Okay, over here this is 30 cm. Jia Yi called it the height. Is that the technical term to use? Okay, amplitude. This is our amplitude. Okay, what else can we tell from this? Kim Hong? Wavelength. How do you choose wavelength and not period? Yes, because it is a displacement distance graph. So on our horizontal axis, it is in distance, meaning it can't be period, because period is measured in seconds. So what is the wavelength? How much? 4 meters. Okay, he said that the wavelength is 4 meters. Take note of the SI of the units over here, meters. So he chose to read from here to here, am I right? So that is one complete cycle, and that is 4 meters. Okay? So we have 30 cm, 4 meters. I'll continue with the rest. So please go back, finish up 1B and 1C. First lesson of next week, I want to go through your TYS questions also. Okay? We have finished this chapter already, waves.